Well, hello everyone. Monday night, and it is the Physicist and Philosopher Hour. We're just a tad bit late because we were talking, and
Yes.
so um, our apologies. Welcome everyone tonight. Already a full room. Thank you, all the moderators. Well, Miss Dr. Albers, how are you?
I'm very well, thank you, Wayne. And how are you?
Doing
And
good. Doing good.
Claudia's fine. I really don't mind.
Okay, well, I'm still that Southern boy. You
Okay.
here in the United States, Claudia, we have this place called Texas,
Hmm.
and it's the South. And so, as there's an old expression is that you can take the boy out of Texas, but you can't take Texas out of the boy.
Oh, that's very interesting. You
So
you a Texan no matter where you go.
exactly, I used to have it really bad because everything was like y'all, how y'all doing? So, and I'll catch myself once in a while, and you hear that drawl come out. But yes, it's just like it's always there.
Okay. Well, that's wonderful.
So
At
I
least
was
you know where you come from.
exactly, and I was born in Illinois. Go figure that one out.
Wow.
so, so how was your week?
Oh, it was good. I've been working as usual, writing
Yeah.
lots of articles. Yeah.
Saw that. Saw
Mhm.
that. We've had a lot. I just want to say hello to all of everyone coming in. Thank you again, moderators, for tonight. So, we had a question. In fact, we've had a lot of questions coming in
Mhm.
from our listeners. And the one that I sent you, effects of a dying star.
Mhm.
I'll read the question. It says, can Dr. Albers provide a detailed analysis of what she believes will happen to our solar system as a result of our dying sun, and what stage are we at in that analysis? It seems this may be something that we will not be able to recover from, unlike previous Nibiru passages of the past. Thank you. Okay, well, there you go.
Yeah.
Yeah,
Very interesting question. There's a lot I can say about that.
okay.
First of all, people talk about Nibiru,
Mm.
passages of Nibiru. I don't think that the system we have right now is the same Nibiru we had before. Because if it had been the same, then we wouldn't have a sun anymore, because this system destroys the sun and, in fact, the whole solar system.
Good point. I've read not Dr. Marshall Masters' books on the Egyptian bronze books,
Mm-hmm.
and read the descriptions of the destroyer coming through. And Claudia, it always described it as being very hot. And I had never thought your angle that it would take from our sun.
Yeah, it can still cause the sun to have an extreme size CME that might destroy the Earth, but in the end, it will suck all the energy out of the solar system, out of the sun. The sun will lose its outer envelope, its atmosphere. All that will be left will be the core. This is what this system does. This is what I believe. This is why it's so large, because it's gone through other star systems and done the same thing to them, and actually absorb these star systems into itself. That's why there are thousands and thousands of objects in the system. It's why it's so huge. This is why it encompasses the solar system, as large as it seems to us, is a tiny little bubble in space for the system. And so what it does, it absorbs whole stars. It doesn't do it quickly. It may do it over thousands of years. But as we know, 1,000 years during 1,000 years is not long
No, no.
in terms of galactic time. So to us, it's only been here, I believe, less than 200 years, somewhere between 150 and 170 years. So it hasn't been here that long, but it's already caused a lot of damage to our solar system and particularly to our sun. But people say Nibiru, talk about Nibiru, and we can still use that name because Nibiru is a rogue planet or
That's
a
what it
rogue
means.
star.
Yeah, that's literally.
That destroys, that causes destruction in the solar system. So in a way, this is what we have. But it's not just one planet or one star. This is a whole system of them. So we could say we have a whole lot of Nibirus in the solar system.
Yes.
Okay,
And
so it's not that we cannot use the name. We can, and possibly in the past we could have had different objects coming through the solar system that caused destruction. Could have been different comets, and people called it Nibiru. That's fine as well. The thing is, what is important about it is the fact that now and then things happen in our solar system that causes destruction. And at the moment, we're having one of these events, but this event will destroy this star system completely. If it's allowed to go to completion, then it will destroy it, it will absorb it, there will be nothing left. The sun will become a core, the earth will become a core. All that will be left of the earth will be the core of the earth. But because it will lose all layers above that. But it will become much larger than it is right now. So the core of the earth will grow to a huge size. It may grow to a size that's larger than the earth is right now with all its layers.
interesting.
Yeah, so what is happening with the sun is there are two things that seem to be contradictory at first, but they are not. The sun is becoming more active. So if we look at sunspot numbers, I've written an article about this, and I actually made a video, but then after I made the video, I realized I need to change the title, so I need to do it again.
That happens. Any writer knows that.
Yeah, so yes. I need to do it again. So, but what it shows is in ice core samples. So in Antarctica, they dig up these cylinders of ice and they look at the radioactive compounds in it. And from it, they can figure out how active the sun was over the last 1,000 years, 2,000 years. This data I came across goes back to about 11,000 years ago.
Okay.
And it shows that the sun was not as active for that length of time as much as it has become in the last 200 years than it was 11,000 years ago. So 11,000 years ago, the sun was a little more active than it is right now. This means that, so the activity has gone straight up from about 1850, exactly the date that coincides with the entrance of the stellar cores. I believe it happened then because we started seeing noctilucent clouds on Earth, never seen before. And that shows that stellar core dust was entering our atmosphere, started entering then. So the solar activity has been going up for about 200 years. We are at a grand solar maximum right now. The activity has gone through the roof. It's grand solar maximum. And that means the sunspots sunspot numbers are at all-time high, solar flares and CMEs in the last
in the last 300 years, because right now we are at a minimum.
Yeah, we are at a local minimum, but at a grand maximum in terms of 10-year averages.
Okay.
Okay. So, but what I discovered is actually happening is at the same time that we're having this maximum, the sun is extremely weak. How can it be both? That's the thing. But the stellar cores are causing both because they drawing energy from the sun. So it's becoming weaker because we know that because the magnetic field associated with each sunspot is decreasing in strength, and the amount of light the sun is emitting has been decreasing since 2011. We know that at least since 2011. It probably started declining before, but we don't have data. So the sun is emitting less light, and each sunspot that it produces has less magnetic field. So it's still producing more sunspots at times, but these sunspots have low magnetic fields associated with them. This shows that the sun is weakening, and it's weakening because the stellar cores are drawing energy from it. If you draw energy from something, it's going to get weaker. But the thing is, what I discovered is that the energy contained inside the sun's particles determines the strength of its gravitational field. And so as the sun gets weaker, its gravitational field decreases. And the gravitational field is the sun's ability to hold on to its mass, to hold on to its plasma. So as the energy decreases, its ability to hold on to its plasma decreases. So what happens is then when a large stellar core first arrives at the sun's corona, that's when it draws the most energy because it's at its weakest. Mm-hmm. And when it starts drawing, it provokes the sun into having these huge increases in activity. That's when we see solar flares. That's when we see CMEs. And then it settles down. It keeps on drawing energy, but the effect is not as strong. And so the sun settles down for a while, and we can see it's very, very low activity for a time. We can see it continue to decline in light emission. And then another large stellar core comes along. And then each time a large stellar core comes along, the sun is more reactive to it because it's weaker.
Okay.
And this is what's occurring. So in a way, the sun will get to a point where it cannot emit light at all because it's progressively weaker, but yet it's more reactive. So a stellar core, a very large stellar core arriving at the sun's corona can provoke it into having a huge CME that is actually dangerous for our planet.
True.
So what is most likely to occur? We know that the sun is declining in light emission. The intensity of light, which means the number of photons that it is able to emit per unit time, is decreasing. So eventually the sun will go dark. And it already goes through periods where it stops emitting light for a certain period of time. It will probably get to the point where it will only emit light for a small period of time. It will just seem to ignite, emit light for a little while, go dark. It will go through that for a while. Eventually, it will become just dark all the time. But even then, if a large stellar core comes to it, it can still cause a huge explosion. And what is going to happen eventually is, I believe we're going to get a solar flash. We're going to get a huge CME, a huge ball of plasma is going to erupt from the sun. It's going to destroy most of the inner planets. Because what it does, if it's large enough, it will just blow off the atmosphere of planets. It will burn up the surfaces of the planets. It will destroy the planets. So this is what's likely to happen even before we get to the point. The surface of our planet will break up. It will break up and exit out into space. The same thing will happen to the sun. It will start losing its plasma out into space. So the solar wind will become denser, and the velocity of the solar wind will decrease. That's likely to happen. It will keep on losing its layers. The planets will start losing their layers because the gravity declines and the planet's not able to hold on to its surface layers. So first we'll see them expanding, the surface breaking up, like we see it's happening on Earth. We see the fissuring, the sinkholes, the volcanic activity. You know that the Earth's thickest layer is the outer core. The outer core is made up of liquid rock. Our planet is made out of more magma than anything else. So when the planet starts breaking up, what's going to happen is this magma is going to come up to the surface. The planet will be engulfed in magma, in lava. It's called lava when it's at the surface. So this would be the end of our planet, basically just lava everywhere.
That's going to be a bad day on Earth.
But it's not going to happen immediately. It's a slow progression. In a way, we have time to build, space
to get the hell off this planet.
We have to get off. If this continues, we have to get off this planet. We cannot survive on it.
And I want to point out a little anomaly. I call it an anomaly. And this is what's so interesting about this cycle of the sun. Again, we have a blank disk. I think we are now day 92 into the year of blank disk. But this is what's so unusual, Claudia, is this region. I want you to pay attention to this region right here, because this region, when you look at the data, and we'll go here, and this, I think this is 197 angstroms, I think. Two things. You think that this is a huge sunspot coming in, but it's not. There's no magnetism to it.
Interesting.
Yeah, and that was pointed out this morning. And again, notice this right here, and we'll go back over here to, again, let's go to this one right here. This one will tell us the magnetism. And as you can see, there is none.
Yeah, so basically this shows a progression in the weakness of the sun, because basically we have sunspots with no magnetism.
Yeah, look at that. You would swear that this is
a bright emission from that region. But like I said, already in cycle 23, the magnetic field associated with sunspots was coming straight down. We're now at the end of cycle 24. This was during cycle 23, between 1996 and 2009. Two physicists did a study on this and found the magnetic field associated with sunspots declining. Now we're getting to the point we're not measuring even any magnetic field strength at what looks like seems to be sunspots.
Yeah, and that's what it looked like. Someone asked the question too, Claudia, today. Could you ask Dr. Albers why the southern coronal hole closed up only to the northern? And I went ahead, Claudia, and did a little research on this, and I think we can give people a good answer. Can you see this? The graph pulled up here?
Yes.
Okay, so this is the one that I watched to see where our permanent coronal holes are. And look what's happened here, Claudia. We can see that the belt, the streamer belt, has moved north. And look at the concentration of the coronal hole up here and the dispersion. Now, this is what I found interesting, Claudia. Look at the closed magnetic loops in the southern hemisphere.
That looks strange.
It does. It does look strange. Like, so when every time we get together, what I always walk away with is that the sun is doing things we really don't understand, do we?
Yeah, that's the thing. According to solar physicists, the sun goes through cycles. And when activity is stronger, then this is likely to happen. And activity is lower, then this is likely to happen. But the thing is, they don't admit the fact that we have stellar cores in the solar system influencing it.
Bingo.
So this could be the coronal holes are most likely due to stellar cores approaching the sun. They would make a connection with the sun. They would pull on the sun's magnetic field. This is what I've been saying from the beginning. So if the coronal hole at the South Pole were to close up, then that means that there are no stellar cores approaching the sun from that direction, or no dust approaching the sun from that direction. Then it would still only be coming in through the north.
Now, Claudia, as you were talking, all right, see the date here? 7/7, right?
Yes.
Okay, so it's 2 days behind. I don't remember. Anyway, I just think that we get so many different.
This is stereo. That's the thing. You have to realize stereo and SDO have different perspectives. SDO sees from Earth, while stereo is almost from behind the sun, opposite direction of Earth.
Different pictures altogether. I'll tell you, it's crazy stuff.
Different perspectives.
It's like, wait a minute. So I just thought I would bring that out so people can see that.
Yeah, but I still see permanent coronal holes at the North and South Pole. I don't see that changing. It may have moved a little bit to one side or another, but they're still there. I don't think they're going to go away because...
I don't think so either.
I don't think so. In fact, what is going to happen is the sun will become one large coronal hole, the whole surface. It's already happening. You can see that the density of the corona is decreasing all the time everywhere on the sun. It's just that the North and the South Pole got to extreme low density before the rest.
Yes. And we went on Friday night, I took everyone and told them how to begin to really look at the charts, how to read the data. And it's still remarkable to me. We're seeing changes that I think are just, well, it's quite amazing to watch.
It's just surprising to me when I hear solar physicists talk about the sun and they never notice how the corona is disappearing. How can they not see it? I don't.
Well, there's the question right there. They don't see it, and they don't seem to be too amused about it either.
Or if they do, they won't say anything about it.
Yeah, so I'm going over here to SDO directly, and I want to pull up again so we can get, this is the one I want to actually pull up. So did you see that one? Can you see that graph?
Yes.
Claudia? Okay, so here's the thing. We don't see any magnetism in that region here. Maybe it might develop, but I just find it so large that this dispersion area here, that it doesn't have any magnetism to it. It's just...
Yeah, well...
like, why?
It has low magnetics.
Yes.
That's to be expected. Like I said already in cycle 23, we had declining magnetic field associated with sunspots.
Yes.
So it's to be expected. But it also means that we can basically, sunspots, because we usually told that the sunspots appear because of the magnetic field. But maybe it's the other way around. The sunspot, it's likely to be something else. The sunspots are a sign of higher activity, but they appear there. Why? Because there's something causing the sunspots to appear, and it seems to be actually stellar cores maybe causing the sunspots to appear. And then once the sunspots appear, then we may get the magnetism that's below there sort of poking through. You see, because they deny the fact that we have stellar cores influencing the sun, everything they say about the sun is turned upside down, and they don't follow the fact that for every effect, there must be a cause. There must be something causing everything that's happening with the sun. And I believe the stellar cores is the main reason why any of this is occurring with the sun. There you see that connection there. That's usually the connection we see that the sun makes with the stellar core, or actually the stellar core makes with the sun.
And look at this huge ribbon. I mean,
Yeah.
that's what I've been pulling up here, because this is an unusual solar tornado there. That one,
Yeah.
yeah, you're looking at the thing. I'm going, now, wait a minute. And that's what I'm trying to pull up into the different spectrums here and see if we can actually.
Yeah, that's a good thing to call it a solar tornado. Do you know that the same thing happens in our atmosphere? We sometimes get these tornado connections. I'm starting to think that some of them are actually caused by stellar cores connecting with our atmosphere. They cause this kind of thing to happen. They will induce a severe storm in the atmosphere. That definitely looks like a connection.
Yeah, it does, doesn't it? I was just trying to pull in the different spectrums. You can really see it here.
Yeah, you don't see the stellar cores in every wavelength because they don't emit light in every wavelength. Sometimes they don't emit any light at all. And if they are in front of the sun, somehow they are not seen. It's just the way these images work, because the coloring is computer generated.
Mm-hmm.
So we only see them on the sides, basically. In the front, the images seem to be designed to show a lower part of the corona, not the top, a lower part. And somehow that means that the stellar cores that are there in front disappear from the image.
You know,
and they're very difficult to see.
I've told people, you follow these long enough, and you're going to start seeing stuff that Claudia, I don't argue with people anymore. It's like, how do you tell them that our instruments are picking up objects, anomalies that, well, they're just not normal?
They're just not normal. And the pictures that Scott has found over the years are undeniable. They show there are three-dimensional solid objects there. I mean, I love to show that one where the object is actually striped, and the stripes are curved because they follow the curve of a spherical object. It's undeniable, Wayne. They are there.
It's almost like they don't want to see it.
That's right. The thing is, they will lie to themselves if they have to. So they will see it and they will tell themselves, no, it's not there.
This one is just so pronounced. I mean, I see a lot of them many times dancing with the filaments, but this one is just so pronounced. And again, you think that this is a huge region right here.
Yeah.
Well, we live in different times for sure. And
well, we certainly have a higher electric field at that point. That's why we have higher emission. That's another thing that solar physics denies, and that is electric fields. They will talk about magnetic fields, and they forget that where there's a magnetic field, there is an electric field. First of all, they are induced electric fields. And there's the fact that a magnetic field is caused by a moving electric field. But they want to talk about magnetic fields and ignore electric fields.
And, you know, the more and more when we look at the electric universe, I keep on thinking, you wrote a paper this week on gravity. And can I pull that up? Would you like? Okay.
Yeah, I just wanted to talk a little bit about the basics.
Yes,
because I noticed that some people find it difficult to understand what I've written about the new theory I came up with called electrogravity. They find it difficult to follow the concepts because they're missing some basic concepts about gravity. So, you know, and I believe that everyone gets this in high school, but somehow they're not teaching people properly, or people maybe missed it. I don't know. But I did teach this to my first year students, this type of thing. I did a little bit of an introduction, and and some of them were so behind in their ideas that they couldn't even picture the moon being in outer space. That's the kind. I did have some students like that. So I had to make sure that everyone was up.
We got listeners like that. So, just kidding, everyone. Settle down. So let's talk about gravity.
Okay. Mm-hmm. So I start with a man standing there and dropping something. Okay. And this is what I did for my students as well. I would stand in front of them in the class and take a duster in my hand and drop it. Bang, on the floor. And I said, why did the duster fall? Okay. And the reason why it falls is because the earth attracts it. The earth pulls on it. And we have to go back to basics and realize that a force is a pull or a push on an object. That's what a force is. It pulls or pushes. So the ball falls because there's a force on it. The earth pulls on it. That's why it falls. If we go out into outer space somewhere where there's no massive objects, no gravitational fields, and we drop the ball, nothing happens. The ball stays where it is because there's nothing to pull on it.
What I don't understand, and yeah, I do understand, but it's a question I'm putting out there for discussion purposes, is that we live on a sphere that rotates, right? It consistently rotates. But gravity seems to be universally or on the planet to be applied, but that's not necessarily the case. And I guess what I'm questioning here, are there different intensities of gravity?
Well, basically the gravitational field varies. So you get pulled in more strongly at a certain level than another.
Correct.
So
That's what I'm trying to do the representation here.
If you move down towards the center of the earth, if you dig a tunnel, then the gravitational attraction as you move down will decrease because there's just less mass below you. So at the center of the earth, there's no gravitational attraction. Well, that's according to Newton's theory.
And I don't understand that.
No one has gone there to check.
That's right. That's going to say no one's drilled all the way down yet.
But this is Newton's theory, okay? So in this, I'm using Newton's theory. And my own theory is different from this theory. Okay, I go into energy, photon energy, which then determines the gravitational attraction. So, but according to Newton's theory, which is the basic theory, but even if it's not quite right, it gives you the concepts to go further.
Okay.
So in that way, it's important. So things fall because there's a pull from the earth. Okay. And we can have different trajectories for things. We can just drop it like we see in figure 2 on the left. That man just drops it. And then the next one, we see someone throwing something upwards. And what happens if you throw something upwards is that it starts with a high velocity upwards initially, and then it slows down as it moves up until it stops. And then it accelerates moving back down. Why does it slow? Because there's a force pulling it down. It's like if you're running along and someone comes up behind you and starts pulling on you. So you're going to slow down.
Yeah. So while the object is going up, there is a constant force that is actually pulling on it the whole time.
Yeah, there's a constant force constantly pulling it back down. That's the earth pulling on it. That's gravity.
Okay. And gravity is represented by F, right?
Yes.
Okay.
F, we always use the letter F for force. And so I put F and then the little word gravity to mean this is the gravitational force.
Okay.
All right. Now, so that would be the second diagram. In the third diagram, you see that it follows this parabolic, this curved path. Okay. No, don't move down yet. We're still up there.
Slow down, Steiger.
Yeah, let's move it. Yeah. Okay. Now you see it follows this curved path. The reason why it follows its curved path is because the man didn't throw straight up. He threw it at an angle.
Gotcha. Okay.
And when he throws at an angle, it's got a component of velocity upwards and another component horizontal. So there's no acceleration along the horizontal direction. So the object will keep on moving with the same velocity throughout the time that it's in the air. The same velocity. There's nothing pulling it back, so it will keep that velocity. But the gravity will still pull it down. So what happens is, as it moves horizontally, it will first move up, but it will slow down, and then stop, and then accelerate back, but it will follow that curved path.
Interesting. Okay.
Yeah. And it follows the curved path. That is, it goes up and comes down for the same reason, because the Earth is pulling on it all the time.
All right.
Okay. So now we can move to the next one. Now, until Newton, people thought that the force that keeps the planets moving around the sun, or the force that keeps the moon moving around the Earth, was different from the force that allows objects to fall towards the Earth. They knew there were forces causing that, but they didn't know it was the same force. Newton was the first one that said these are the same force. It's the same force. So what I have here, I have the Earth and I have the Moon. The Moon moves in a circular, or almost circular orbit around the Earth, not quite circular. Now, what I drew on there is a rocket, and this is a failed rocket launch. In other words, the rocket is not launched with enough speed to go into orbit. So what it does is it follows that same curved path that we saw in the image above there. It goes up and it comes down. It's a failed rocket launch. Now, notice that the moon is doing exactly the same, except the moon, the curved path is wider.
Yes, okay.
So the moon is following a curved path around the Earth as well, just like the rocket. But because it's wider, it never comes back to Earth. So if the moon was not being affected by the Earth's gravity, it would move in a straight line. It would move along that red arrow we see pointing down. But because the Earth attracts it, pulls it in towards the Earth. That's why the moon moves in that curved path. So if an object moves in a curved path, that means it's under the influence of a gravitational field. If it's not under the influence of a gravitational field, keep on moving in a straight line.
While you were talking, can I ask a question that I have here? So is gravity dictated by rotation?
No. It doesn't matter whether the Earth rotates or not. It will still pull the moon in. Gravity is determined by mass, according to Newton's, and the distance the object is from the point that's generating the gravitation.
That's my point, though. But if it seems like everything that I know when I observe in our universe, our solar system, is that every planet, every moon is spinning, thus creating a gravitational field. And I still don't understand how the moon, now I understand how they say in the physics that the moon is in that perfect equilibrium line between the Earth's gravitational pull and the sun's. Okay, I guess that's true.
It does not depend on how an object rotates. In fact, the Earth's rotation decreases the gravitational attraction at the equator, because the rotation tends to cause objects to move away from the center of the Earth. But it's a very small effect, and it's the strongest at the equator. But rotation has nothing to do with gravity, with the strength of a gravitational field. And you can see that because, for example, I think it's Venus that has an extremely low rotational period.
Yeah, once every 287 days.
Exactly. But yet its gravitational attraction is about the same as the Earth's.
Yeah, and then one odd thing is that at the ionosphere, it's moving at 4 days rotation.
Mm-hmm.
That I don't that has to be a hell of a shear taking place, Dr. Albers. I mean, at some point in that planet. Anyway, I digress.
Yeah, there's something very strange about Venus, but the fact is Venus does not seem to generate a magnetic field like the Earth does, and that changes things as far as its ionosphere goes. Because then the sun has direct contact with its ionosphere, and its magnetic field is thus simply an induced magnetic field due to the solar wind interacting with its ionosphere.
So can I ask you a question? So when we see asteroids, the ones that are particularly the ones that have passed close, does an asteroid within itself, and even though the mass may not be large, have a gravitational field attached to it, although it may be very weak?
Yes.
Okay.
All objects with mass will generate a gravitational field.
Okay.
The stellar, you see that according to Newton's law, every object in the universe that has mass will generate a gravitational field.
Interesting.
The problem came then when the stellar cores started being observed in the sun's corona, and they were not obeying that law. Then I had to come up with, that's why I came up with a new theory, because then I decided these are dead objects drawing energy, therefore low in energy, and that means gravity is determined by the energy or the photon energy inside the particles making up an object.
So as I just said that, and as you just finished your sentence, I'm thinking to myself, okay, so gravity is not dictated by rotation of mass, but that the more I think about this, the more I see an electric connection, more than simply Newton's thought that the first principle, the first law was gravity itself. Actually, it would be electric, right?
The thing is, there was no electricity when Newton was looking at this. There were, I think they knew a little bit about magnetism. There was something about static electricity was known, but they didn't make the connection. This didn't happen until 18-something that Maxwell came up with his theory of electromagnetism.
Dr. Albers, you just triggered something. So we have Newton, who makes the observation, who we could say was the first observer, begins to apply what we would call cognitive rational thought, logic, to what he observed, recognize that it doesn't matter what the weight of the object is, its rate of fall, it's going to be equal to the pull of gravity itself. Do you think that held us back a couple hundred years when people were convinced that Newton was right and began to apply his theory? But then when electricity came into the picture, it seems like then that was the first rub with science.
Yeah, the thing is, we have not been told about the connection between gravity and electricity, because the theory I came up with uses both. I don't think one can exist without the other. And I'm starting to develop new ideas I haven't written about anymore. And that is the fact that the electron seems to be extremely important carrier of energy. And the reason why they don't want us to know this is because, first of all, once this is understood, you can easily understand how you can use the Earth's gravitational field, which is aligned to an electric field, to navigate inside the Earth's gravitational field just by manipulating electrons with potential differences. You can move up and down and across just by manipulating electrons. And you can extract energy out of it just like that, free energy.
So if you have an atom, right?
Mm-hmm.
The atom within itself spins, correct?
Mm-hmm.
That would be gravity within itself, wouldn't it?
Yeah, the thing is, why all charged particles spin is because you cannot get an electric field without a magnetic field. I don't usually go into the magnetic effect because it complicates things, but basically you actually have three fields: the electric, the magnetic, and the gravitational, all together everywhere. You don't get one without the other. The three are always together.
Electric,
And
gravitational, and magnetic, right?
yeah, it's the magnetic field that causes things to rotate. So
Yes,
this
yes,
is
yeah.
why everything in the universe rotates, because you have a magnetic field.
We learned that in the second, as children, that when you see a magnet and you get polarities, what do they start doing?
Mm-hmm.
Excellent, excellent. And in fact, that's how we figured out electromagnetic electricity. The same thing.
Mm.
Interesting.
Yeah.
So getting back to the moon, then I can see the equation, although it's not clear. I'll be candid with you, Dr. Albers. I'm still not there.
What I want you to see is the connection between the two curved paths.
This one here.
Everything that's affected by gravity will follow a curved path. If the Earth had not pulled that rocket back, it would have just gone up in a straight line. But because the Earth pulled it back, it followed a curved path back to Earth.
Okay.
The moon follows a curved path as well. If the Earth was not pulling on the moon will just move away in a straight line. You would never see it again. But
it would be a Nibiru.
Exactly. But because the Earth is pulling on it constantly, it keeps moving in a curve. It keeps moving in a circle around the Earth. It's because the Earth's pulling on it. So this is why I say it's in free fall. It's falling towards the Earth, but it's moving at very high speed, so the curve is very wide. And
that's what Gene Cernan told me. He said, Wayne, he said, when you're out there walking in space, he said, you're not floating, you're falling.
Yes.
That's what he said. And he says, you don't realize it, but you're falling really fast.
That's right. And you know why the astronauts on the ISS do not are floating? It's not because there's no gravitational field. There is quite a strong gravitational field even at that altitude. The reason is they are falling. They are in free fall. The same thing will happen to you if you are an elevator and the cable breaks. The elevator will be in free fall. You'll be floating in it until it hits the ground.
But guess what? You're falling the whole time. You may think you're I mean, the thing with the vomit comet. Yeah, you're weightless there for a couple of seconds, but you're going to pay the price for it. So
yeah.
You wrote an article here. I was reading on the Planet X debris field, and I just thought that this one was so interesting because I was interviewed by April up on her radio station up in Canada. Mm-hmm. And when we think about the debris field, I contend that, Claudia, we're in a debris field. I mean, our whole solar system is, right?
Absolutely. We are definitely, what has occurred is that starting from 1850, we started getting hit by this debris field, which was mainly dust, small pieces of rock coming into our solar system. And they started almost at that time, that's when they started reaching our atmosphere. That's why we started getting noctilucent clouds. And that was stellar core material coming into our atmosphere. And stellar core material is low in energy, so it draws electrons, which are higher in energy. And when that happens, ionization starts occurring, and there's light emission as electrons are captured by matter. And this is what we then get. We get clouds that emit this very strange light. Look at it.
Yeah.
Orange, red, pink, there's magenta, there's dark blue, all kinds of colors being emitted from this cloud. This is not a native process to our planet. This can only occur if strange matter comes into it.
I could see how the ancients would see that as a dragon, a fire-breathing dragon in the sky.
Mm-hmm.
I mean,
the thing is, a comet, if it comes very close to Earth, would probably have a similar effect, not as strong as a stellar course, because comets will come from outside the solar system, have different energy levels. This is why they absorb electrons and ions inside the solar system. So if one comes very close to Earth, it will draw electrons from the Earth's outer layer. So there will be electric effects, ionization, all kinds of things like this would happen. So I'm sure the ancients saw things like this.
And thank you, Dr. Albers, because there is so much debate, so much discussion on the whole Planet X Nibiru thing. And I like the fact that what you point out here is that we don't stop, and I don't hear these channels talk about this. They don't talk about the science effects, that the fact that there are electrons that are being excited here, that you have mass pulling from one mass of its electrons being transferred to another. And that has a natural effect, right? You're going to see it in the atmosphere.
Exactly. That's the thing. You have to have a reason for something happening. We cannot say, say this is occurring. We have these strange clouds. Okay, how are we seeing these clouds? What's causing this? What is the mechanism? So what scientists nowadays have done to hide these things is say, give it a name, say, oh, this is this cloud, and this is what it is. Like with noctilucent clouds, they say, oh, they're luminescent clouds.
Yes.
And they're in the upper atmosphere, and they're made of ice crystals. Wait a minute, how are ice crystals emitting light? Because luminescent clouds means it emits light. Why hasn't anybody asked this question?
Because on the very same side of their mouth, they're saying, well, now, when you look at a rainbow, understand that you're just seeing light being refracted in the atmosphere through water molecules. Now we have ice crystals generating light.
Exactly. The thing is, they're not reflecting. They are emitting light. And that means an energy transfer mechanism. Where's the energy coming from?
Well, you're going to get technical on us.
Exactly.
I mean, that's your problem. Well, okay. So,
so here I actually remember we were talking about the ACE data.
Yes.
And so I actually comes from Discover, and I looked at the density, and I found these spikes in the density. Look at this. This is not normal. The solar wind particles, the solar wind's not supposed to cause these spikes. So what is this actually? This, to me, looks like debris coming in. A stream of debris comes in, short amount of debris comes in the solar wind.
Yeah.
Impacts the magnetosphere. That's stellar core debris or dust coming into our atmosphere. And I think this is one of the things they're trying to hide with that addition of colors on the ACE solar wind velocity simulations and things like that.
This is quite remarkable.
Yeah. This happened on the 12th of June. This is where I caught it, probably happening a lot more often. I caught it on the 12th of June and on the 16th of June at just about midnight UTC, both times.
Look at that. Well, that would suggest almost then a pattern.
Yeah, well, I don't know. I probably have not caught I haven't sifted through enough data to actually say that it is.
Now, when we talk
Um,
about density, we're talking about densities of protons, right?
yeah, this is proton density, yes. So
Okay.
this is a huge spike in proton density. This is just not normal. The solar wind varies. It's never a sharp peak like this. It's impossible. The solar wind doesn't behave like this.
I mean, look at that's hello. It's like there's something not right
There's
there.
something not right there.
Yeah.
And I think this is what they hide. The signs that something is going on here that's not just the solar wind.
Okay. You see, this is why it's so important that, you know, what I see is that you've introduced, and as you have said, this is your hypothesis, but I'm telling you, this, Al, is everything, whether it's Einstein, and no matter how far you want to go back, this is how theory becomes science.
Yeah, the thing is, what is powerful about what I'm doing is that I'm using observations. I am fitting my ideas to what is actually happening, like these colors. These are not natural.
This is
Let's look at the top two first, Wayne.
okay.
You see that the lightning there on that side is almost reddish on the left.
Over here, yes.
While on the right, it's purple.
It is.
How is lightning different colors? Because as far as I remember, lightning was supposed to be just white.
Yes.
White. But we're not getting white. We're getting different colors of lightning. How's that possible? Well, it could be with the gases in the atmosphere, but as far as I know, our atmosphere is pretty mixed. It should just be, a certain amount of oxygen, a certain amount of nitrogen everywhere. So how are we getting different?
And the heat that a lightning bolt puts off, I didn't think it was regulated. It's like 50,000 degrees.
Yeah, it's extremely hot. It heats up that, the air actually becomes plasma as the current conducts through it.
Yes.
And it becomes extremely hot. This is actually what's causing the sun to emit light. Just imagine this in the sun's atmosphere, but so intense that it's all the time, everywhere, just about every single spot is filled with this.
Amazing. Yeah. And then we get this.
And then this magenta color in the sky. This is not natural to our planet. This, I believe, is all signs of this debris coming into our atmosphere, interacting in our atmosphere and emitting light in different colors. This is what my conclusion about what's actually occurring. And even the lightning, this is likely to be due to also stellar core matter in the atmosphere, possibly larger objects now, causing these storms, these lightning storms, because as I've said before, they will lead to intense storm activity because they will cause extreme low pressure regions.
And when we talk about stellar cores too, Dr. Albers, I keep on thinking that we could be seeing objects that could be a couple miles across. We could see an object that could be a couple thousand miles across. But when you think that the diameter of the Earth is what, 24,000, almost 25,000 miles, an object that it would even be 1,000 miles across would still be only 1/25 the scale of Earth. It would be small. Wow. And it's not visible in the normal light. Well, the light that we see from our sun and our atmosphere, it's plausible. It absolutely makes sense to me.
Yeah. And don't forget, what we have most of the time is simply dust.
Yeah.
Just stellar core dust, because the inner solar system is filled with it now.
And, I'm in my early 60s, but as a child, when I worked on the farm, we grew up on a farm and we would see the sunsets. Mm-hmm. They weren't like this.
That's right.
They weren't. And so, yeah. All right. So this is one of the,
there it is.
There it is.
Yeah.
I keep on hearing, people say, no, well, no, that's just a cavitation. And I'm going, well, explain to me how that cavitation is working again.
Well, how does a cavitation maintain its perfect spherical shape as it moves away from the sun? Because as far as I know, if it was a CME, then it would disperse, so the cavitation will get larger. We don't see these objects getting larger, do we?
No, actually, we see them. Listen, I have seen this on Secchi as they have now departed the inner solar system heading out. And Dr. Albers, they're still cylinder condensed spherical objects.
Yeah, and the thing is, I don't believe they actually get very far. They come back. They are ejected at the time. They probably, I don't know where they move out into the solar system, but I think they come back to the sun if they've been to the sun before. It could be they go to the other planets, but I don't think they will leave the solar system. There will be energy bound to the solar system once they come into it.
Yeah, I was just thinking you probably have to get past Jupiter. Jupiter is like a breakwater. It's like, it's not going to let you back out.
I'm sure Jupiter has caught a lot of these objects.
I would think that you would be probably correct on that. Yeah. Wow. So, and here we go. Is this the rift?
As always, I usually try and bring it back to what these objects are doing. They are lowering the Earth's energy. And by lowering the Earth's energy, they are causing the Earth to expand. So it's going to break. The surface is going to break. This is what we're seeing happening here.
And I do know a little bit about seismic activity. And when I see this, Dr. Albers, I keep on thinking there are tremendous forces at work here. I mean, this is energy on a kinetic scale that I can't even begin to imagine.
Yeah, the surprising thing is, Wayne, that often we hear about the Earth just splitting without even hearing about an earthquake occurring. Yes. How is this possible? This sort of thing is supposed to happen when we have a huge earthquake.
And instead, it's like
people wake up and they find this huge fissure in their way. And that's no earthquake. How is that even possible? Because the Earth is opening out. You don't expect an earthquake if the Earth just moves apart.
And by the way, as I was looking at this, I immediately got the mental image of what we see with fissure number 8 over in Hawaii right now.
Uh-huh.
Same thing.
Yeah.
It's just got magma coming up at it at a high rate of
that's a really bad thing happening there.
I don't know what's going on over there, but that one is
that's
definitely
really serious to me. That's going. The thing is, I believe that's going to happen in other places and more. And it's a sign that the Earth has reached a point where it's being deeply affected. Don't forget, it's been 170 years.
Yep.
And it's reached a point where the effects are getting stronger. We're seeing more cataclysmic type events occurring. And like I said before, it's always a slow progression. But what is happening in Hawaii tells me we're in an advanced state now.
And I keep on thinking that this is an accumulated effect that's been building up. Even if you take the Carrington event as the tripping point, 157 years, that's a lot of energy.
Yeah, it is. In terms of our lifespan is a long time, but like I said before, in terms of the lifespan of a star, it's a very, very short amount of time.
That's my goal, Claudia, to become a sun.
Okay. That's a good idea.
I just want to tell you that's my goal. Well, another hour has literally come and gone. I just want to say thank you. I know I'm just looking at everyone in the chat rooms. I
enjoyed it. I really enjoyed this.
You really got this thing about teaching. You're pretty good at it. You got to look into it.
Thank you. I actually enjoy teaching so much.
Well, as again, I recognize so many of the names in here. So it's like this is class, you know.
That's
7 o'clock for me on Monday nights is that I'm going to go to class and I'm going to learn.
mm.
And I hope that's what people are doing. I know that many of them are because by the comments. So, well, is there anything you'd like to close out with?
Well, if there are, I'll answer any more questions if there
Yeah,
are
send them
any.
on. Send them on.
Yeah.
I want to thank, by the way, Chris from over at the Forbidden Knowledge channel. Next week, we're going to be showing, he has a large collection, Claudia, of the stellar cores. And it tells me that people are listening, people
Yes.
are thinking, and instead of criticizing, they're allowing cognitive thought to come in and say, okay, well, let's look at this. Claudia, this is how I look at it. When a person becomes so closed-minded that they immediately reject another person's theory or thoughts, it tells me that that mind is trapped because they're trapped into this illusion that man knows everything. And actually, we're still learning, right? Scientists are still learning.
Yeah, I think the stellar cores are supposed to tell us, look, life, the universe is not what you think. Look.
Yeah.
It's supposed to hit you between the eyes. What is that thing doing in the sun's corona? That's supposed to be impossible.
No, exactly. And I keep telling people if they would just simply listen and consider, let's say that we wake up one day and there is a planet that has arrived on our doorstep. You're not going to have the fear factor as much as if you go back and say, all right, wait a minute, now, Dr. Albers said this. This is what I need to begin to look at. It takes the fear factor away and allows science to come in and quash that, Claudia. That's how I see it.
Yes, the thing is, Wayne, the planets have arrived and they're out there, close to our planet. We know they are there. There's this lady from Universal News Media or something that she's been showing these on FAA cameras. JFP has been showing them. They are there. The sun simulator system is there and the chemtrails, so we don't see them clearly.
Yeah. And go ahead.
But they are there. That's the thing. It's just one of these days, the sun simulation system may fail, and then you will see a huge planet on the horizon.
As you were saying, what will take that, Claudia, will be a Carrington effect. I think it will short the system, and then people are going to walk out going, where did that come from?
Yeah, and what will happen if the sun simulation system will probably have darkness as well, because I think they're actually causing our atmosphere to look blue, because our sun is much weaker. It's going dark now and then, completely dark, not emitting any light, so you wouldn't see the moon either. You wouldn't see any planets. Yep. So they're using holograms, and they're lightening up our atmosphere, and probably only the lower atmosphere, not the upper part. So it looks to us normal, but nothing's normal out there.
That is a fact. I have seen it enough myself. I have photographed it, as Scott has, and we know it. So, well, Dr. Albers, thank you. Thank you. It's always a privilege to sit in your class and to learn. Thank you, everyone, for coming in, and send the questions in. And Dr. Albers, we'll see you next Monday night. All right, everyone, you be good, and we'll see you during the week. Make sure to go over and subscribe to Dr. Albers' channel. I left the link. You've got books over on Amazon still, correct?
Yes, and Scott's about to put up the part 2, but we decided to break it up and make it a little bit smaller.
Okay, good. So, folks, this is how we learn. And I can guarantee you, if you'll just open your mind and start applying the logic that Dr. Albers teaches us, you're going to be the smartest person on your block. All right. Everyone be good. Claudia, hold on as I exit out. Thank you all. We'll see you again next Monday night. All right. Be good.